But anyways, I wanted to talk about the intersection of two things that has always excited me. And of course, the first is robotics. This is a robot group, and everybody knows who this guy is, and he's responsible for getting me interested in robots because of all the cool stories he wrote. Um,
I'm sorry, that's you're good at saying who he is.
Isaac
Isaac
Asimov.
Asimov.
And now again, I cannot show PNG files on your computer.
Oh yeah, you can. Just,
How?
just click.
Yeah, and so Isaac Asimov, I hope everyone's heard about him, but
Yeah.
he wrote a lot of robot stories, and he's famous for the 3 laws of robotics. Basically, don't harm people, obey what people tell you to do, and don't kill yourself. And so this is just a humorous cartoon about his stuff. Another guy who really influenced me and got me interested in artificial intelligence is this guy. A lot of people don't recognize him. His name is Martin Gardner. And he wrote a column in Scientific American called Mathematical Games, I think. And I just loved math and games and puzzles. And one article that he wrote, which was republished in one of his books that I would read, really caught my attention because it was, I think I have, I lost my, he wrote an article, I think I have a copy of it here, on how to build a game learning machine and teach it how to play. And I thought, wait a minute, you can have a machine that's intelligent and actually learns. And I thought this was really cool. It's a great article. Again, it's in the Google Drive, which I'll post a link to. But he invented this new game called Hexapon. It was basically a super mini chess. And the idea was really simple. You would take a bunch of matchboxes, and on each matchbox, you would represent what the state of the current game was. And you would put different colored beads that would represent the possible moves that the computer would make in that particular position. And the idea was you start the game off and you select a randomly colored bead and the computer makes that move, and then you make your move, and then it goes back and forth. And of course, it's probably going to lose because it doesn't know anything at the end. But the beauty of this is the reinforcement learning involved. If it won accidentally or on purpose, you would reinforce that behavior by adding another colored bead of the same type for each of the states, reinforcing so the next time it gets into this particular state, it's going to statistically do that more often. And if it lost, you would penalize it by either adding more of the other colored beads or removing that bead, so it wouldn't repeat that mistake. And it learned pretty quickly. It's a simple game, so I think after 11 losses, it slowly learned to play a perfect game. And I thought this was totally cool. And so, of course, I didn't have access to matchboxes. And he tried to apply this to like mini checkers, mini chess. And it was just a really cool thing. So
what's the vintage of this? This is from the 1980s?
70s, 60s.
Using neural networks?
It wasn't using neural networks. It was just simply matchboxes and beads. If you would just randomly play, and so I didn't have matchboxes, but I had a lot of these, egg crates. And I also had a lot of these, colored beads. It's great having sisters. And so I decided I'm going to do the same thing. And so I would, instead of matchboxes, I would fill these egg crates with different colored beads, and I would make up my own games. Of course, I did hexapon, I did the mini chess and mini checkers, and I thought this was so cool. And I remember announcing, I'm going to solve checkers. And so I figured out, well, why not? This will work for any particular game. And so I started really simple. Why it worked for mini checkers, why can't we do real checkers? And so I started getting egg crates and beads and writing out, and I pretty soon realized, oh my God, checkers is just too big to make a learning computer out of beads and matchboxes. Ran out of beads, ran out of egg crates. What's really cool, it's sort of sad because somebody else actually solved checkers first. I wanted to be the one to do it. This is a really good book by Jonathan Schaefer. He worked, I forget which university he was at, but he decided he's going to solve checkers. And one of the AI techniques that was popular in the day was simple minimax algorithm. And minimax was applied to chess, to checkers. And the idea is, going back to this, it's you assume if everything in this row, if I make this move, what can my opponent potentially do? And I want to minimize the damage that he can do at, say, this level 3, and I want to maximize the score that I can get here at level 2, and so that's called minimax. Lots of advancement in this, alpha beta pruning, lots of heuristics, a lot of chess programs were written, and he eventually solved checkers. But just to give you an idea of how big that problem was, here we go. From his Chinook page, just looking at the total number of positions in checkers, I don't know how many tons of egg crates it would take and how many beads to do this, but we get, I can't even pronounce this number. Here's billions, trillions, quadrillions, so like 500 quintillion positions in checkers.
A lot of beads.
That's a lot of beads. Now, what's amazing is the fact that he solved this in the sense that for any given position, Chinook will play the God's perfect move. And you might ask the question, well, with so many positions, how can you have a database this large? It turns out using alpha beta pruning for a minimax search, you really only need the square root of the number of actual positions because you can quickly eliminate most of the data. And exploring branches where you make a stupid move just get eliminated because you realize quickly, if I make this stupid move, I'm going to lose, so I'm not going to do it. So you don't really have to enumerate the entire search space. As an aside, I know there's lots of different definitions of what artificial intelligence is, and one that I like is minimizing searching the entire search space to find a very, very good answer. And most problems that we apply AI to, there's huge search spaces, and you can't brute force it. And so I like the idea that intelligence is not brute forcing and coming up with something clever to solve a problem that ordinarily would be absolutely impossible. So really quickly, I'll show a picture of different AI categories, and mostly to illustrate that what's the difference between AI and ML is a common question. And the simple answer is machine learning has the word learning in it. Artificial intelligence is intelligence. It does things that are smart. And examples are things like a simple PID loop is artificial intelligence. It takes the entire search space of what's every state that this system can be in, and I'm going to decide to apply to some motor or some, based on feedback with a simpler algorithm, so I don't have to exhaustively decide what I'm going to do in every situation. I'm going to use this intelligent algorithm to do something a little bit more smart. Alpha beta pruning for minimax search is another example. Learning is that's what it is. It's you're doing something, you're getting feedback, and you're going to change. And this gives some ideas of machine learning. Now, this inner circle, deep learning, I personally don't think should exist because it doesn't really do anything. It's not a paradigm shift in any way whatsoever. It's just we're learning a different way. And there's a lot of different ways to learn. Lately, everybody's with LLMs and neural networks, but that is not the only tool in the toolbox. And so today I'm going to talk about two of my favorites, Bayesian recognizers and classifiers and genetic algorithms. And the reason I like them is because they're simple. Like I said, this is the ghetto talk. And you can write software that will run on low-end Arduino Nanos that can do genetic algorithms and Bayesian recognizers. You don't need super cloud computing to do things, which is why I like it. So let's first talk briefly about what a Bayesian classifier is. And this is back in, when was this? 1984. They decided that, oh yeah, AI is kind of cool, and we might want to turn this into a regular conference because it's getting popular. So 1984 was the first annual AI and Advanced Computer Conference. And I was working at a company at the time who was using AI for devices. And they asked me to write a paper. And so I wrote a quick paper, and it was basically, this is how a Bayesian classifier works. The company I was working for was really interesting. It was called Stellar Systems.
It's all single click on the machine.
No, single click. Okay, how do you open a WebP image?
You try photos.
Oh, hey, here we go. And what they invented was a little device that you put your hand on it, and it would measure the length of your four fingers, and based on just those four pieces of information, would identify who you are. And you wouldn't think that's sufficient, but it turns out it was pretty accurate. It was between like 98, 99% accurate, which was good enough for most applications. I think I have another better picture of it. Yeah, here's a better picture of it. What's interesting is I was looking last night for a picture of this, and this is called Lazar Identimat hand scanner. This is the one I worked on. Bob Lazar is a UFO nut.
Did he get abducted?
I don't know, but what's interesting is there was a video of him talking about Area 51 and how they had to use these biometric hand scanners to get in and out of Area 51. So I thought that was pretty cool. I didn't realize that something that I had helped invent ended up in Area 51, but darned if I ever got an invite to go install it.
So the aliens with the 10-inch fingers, they figured.
Exactly.
Yeah, that's what I was thinking.
Maybe it was designed because it could tell humans from non-humans. But the idea behind, it is double click. The idea behind Bayesian or statistical classification is actually very simple. And here's a slide showing an example of three different, say, people or classes. And the idea is you take a number of readings, and here I think we've got like about 8 to 10 samples each of red, blue, and green. And the idea is you just simply take the mean and standard deviation of a particular feature. And then once you have this data, when the system's in use, you go and you take a reading of some unknown person, and you see, you can see my mouse, and if it falls in this area, then you know, oh, you're the green guy, or you're the blue guy, or you're the red guy. Now, interesting to note, when you use more than one feature, sometimes if the features are highly correlated, an additional feature doesn't really give you that much additional classification or distinguishing power or performance. And especially like if you're here in between the red and the green guy, for example, you might not exactly know who it is. Now, a simpler algorithm is called, like, for example, KNN. They just call it the K nearest neighbor. And the idea here is you take a sample and say it's where my mouse is, and you just say, okay, what are the 4 or 5 closest other values? And here it's red. And if you're in between here, it might say, well, it's probably the red guy because I see 3 reds closer than one of the greens. KNN works great. I love it because it's simple. It's just a few lines of code. However, you now need to store all of your data. So what the Bayesian statistical classifiers do is they take all this data, they throw it away, and they just say, okay, I just want the mean and the standard deviation. I just want 2 numbers. I don't want to care about anything else. And so it's an optimization that trades a little bit of accuracy for not having to store a lot of data. I think I have a picture. Yeah, here's an example of using 2 different features. And so basically now the idea is you have a circle or an ellipse, and you measure whatever it is you want to measure, and you look it up on the axis, and you see, is the point inside the red circle, then you're probably the red guy. If it's outside the red and the blue, then it's, well, you're something I haven't seen before. I don't know what you are. And the reason I'm showing this is because most of the classification systems are not in 2 dimensions. They're in like 20, 30, 40 dimensions, because it depends on the feature vector of what it is you're trying to measure. Now, a good example of this is a program that I wrote. Let me see if I can pull it up.
Just use, you don't want to right click. You can use
or
Notepad.
Oh, no, Notepad is good. I hope this font is good enough to see.
You can increase mouse control, mouse control.
Okay, there we go. But the idea here is I wanted to test something really simple. And so I decided, why not use the timings between keystrokes to identify who's typing? And this is really, again, this is a really small program, and I like this because, again, this talk is ghetto AI, and I want to encourage people to do this at home on your own. And this you can borrow and modify to your own heart's content. The idea is I told everybody where I was working what my password is. And I said, but I defy you to log into my computer even though you know what my password is. So I set my password to "this is my password!" exclamation point. And so the number of features, because there's 21 characters, there's 20 timings in between those keystrokes. And so basically we now have a 20-dimensional feature vector. And so the template is just, again, we're just storing the mean and the standard deviation of each of those 20 features. We're not going to store all the data. And the first thing we're going to do is we have to enroll. And enrollment is similar to those red, white, or red, green, and blue dots. We're going to make you type the password 5 times. So I typed the password 5 times, and we're just in a loop, wait for the keyboard to get hit, and then we get system time, and then we add up, and then we store how many milliseconds between those keystrokes. And then we compute the template, which is basically what's the mean and standard deviation for these 20 features. And we end up with 40 numbers, the mean and standard deviation of those 20 numbers. And then we're going to try to break in. And so we just say, please enter the password. And then we let you enter the password, and we're in a loop for 20 keystrokes, and we're going to get the system time, and then we're going to decide, is it you? Again, really simple. We determine how many standard deviations are you away from Chris Meyer's typing cadence, and we want to see what is the distance from the mean. And then you can set, okay, a distance of 1.0 or 5.0, and it depends on, do you want it to be convenient where I might accidentally not be recognized myself if the tolerance is too tight, at the expense of maybe some imposter. If you loosen up the tolerance, an imposter has a better chance of accidentally matching me. But it worked. Nobody was able to log into my computer. So go ahead
and you were.
and I was.
Reliable.
Because,
Unless you made a mistake and you had to hit backspace.
even if I made a mistake and had to hit backspace, it actually learned where I made the mistake. And it turns out I did. That's a good thing to point out. But this is my password exclamation point. So the exclamation point required me to reach over and hit the shift key. And I'm not a super typist. I'm one of those 3-finger typists. And so hitting the exclamation point at the end, for me, sometimes I would miss it. But the beauty of it is the standard deviation of that particular feature was very wide. So even though I would have a wider variation of timing for that exclamation at the end, the beauty of this is it automatically adapted because it's based on statistics.
In other words, it wasn't tight for that.
Exactly. So each feature is going to automatically tighten itself to the accuracy of what your enrollment data is.
And so, yeah, but the rest of it was tight, or was
as tight as I could type.
Right, so an imposter could probably easily do the exclamation point easier
Yes.
than the rest.
Yeah.
But he has to do the whole.
Yeah, but because you're trying to find a point that's encompassed in a 20-dimensional hypersphere, only one of those dimensions is really wide. So you still have to get the rest of them really tight. So that was a lot of fun. So that's a quick overview of how simple Bayesian classifiers are, statistical classifiers, and a simple program that you can use to play around with it. The next thing I want to jump to is genetic algorithms. Genetic algorithms, again, are really easy. And I have some examples here. Really quickly, this is Watson. It's a full-size biped that Dan Albert was working on, and I met him, what, a decade ago? Yeah, it's been over 10
It
years.
doesn't look anything like that today. That's like model build 3 or something.
Yeah, but it was a cool robot, and he had the hardware. And when I started actually at HBRC, I was a software guy, and I thought, hey, this is cool. I want to meet up with some guy who has hardware, because I don't want to build the hardware. So we spent some time trying to get this to walk, and I had the great idea, well, geez, he should learn how to walk by himself. We can use a genetic algorithm for this. Of course, he was reluctant to let me put untried software on this robot that cost thousands of dollars to build.
And broke really easily.
And broke really easily. So we built Mini Watson, which was similar. This is just a 16 DOF Robo 1 biped. And this was, I think,
Circa 2005.
2005, yeah. Well, you'll notice that he's missing part of his left arm, because, yeah, you do break robots when you run untested software, and you're trying a genetic algorithm on it, and it's doing random poses, and it will break itself. But it was cheaper to repair this than Watson. And then we decided, well, why are we breaking this guy? Let's do it in a simulator. So we did it in a simulator. So the first thing, and I'll show a quick video. Double clicking is not running the video on your computer. How do I
Hit
run
enter.
Highlight it and hit enter.
Open with.
Like, use MPG.
Ah, okay. Let me hit pause because I want to highlight that.
Okay, on the left.
There we go. So the idea here, and you'll note that the simulator version is also missing the same arm. That was done purposefully because the idea was he learns in the simulator and then you put that data onto the real robot and see if it does the same thing. And of course, weight and balance is very important for a physical robot. So that's why the model is missing the same arm.
Which simulator is this?
Now this is VREP. I'm gonna spend 30 seconds to say VREP versus Gazebo. I started trying to do this in Gazebo, and after a couple weeks of banging my head against it, got very little, and then someone suggested VREP from Capella Robotics. Within not knowing it existed to this demo took less than 4 hours. That's including understanding it, installing it, reading the documentation, writing a hello world, building a model from scratch, and writing code to control it. So that's
just because it's simpler?
Just because it's much more simple. And it's a question of power versus ease of use. I didn't need a lot of power. I'm sure Gazebo does a lot of things that I didn't need, but it got in my way. So this was something really simple, and you can see it was really easy to get a robot that really matched the real robot. So the idea here is really simple. The data that it uses is a simple frame of animation. And if it needs a second frame of animation, it'll add the second frame of animation. So it's basically 16 numbers saying, here's the angle that I want this servo to be at this time, at this keyframe. I didn't even bother to specify the time between frames. I just set it to 1 second. And this was a simple task. And the idea here is it has a IMU in it. At the moment, because it's laying down, the z-axis is pointing straight up to the sky. And I wanted it to learn by itself, turn z to negative. In other words, flip over. Because I figured that's the first step. If a robot falls down, you have to go face down because you can get to a standing position more easily when you're face down. And so here he is on his back. And what's going to happen is he's going to randomly generate a frame of animation, and then he's going to try it, and then he's going to learn from it. And I'll talk while it plays. Yeah, so he does something at random, and now he realizes, well, the z vector changed by how much, and it knows it wants to negate the z vector, so it's going to try something to maximize the change in the z vector. Now, usually genetic algorithms, it's a simple hill climber. It's going to do stuff at random until it sort of accidentally goes in the right direction. So here you can tell, well, we've got almost, 80 to 80-ish degrees. So it's going to try something similar. And then each iteration, see, it's a little bit more, 90 degrees. And it's going to slightly modify what it's found was the best so far. And it's a simple hill climber. Eventually, it will find a local maxima or minima, depending on how you've written it. So it learned, bend your legs a lot. So it bent that one, it bent the legs in the wrong direction and had no effect. So now it's going to, there it goes. So it learned bend the legs and bend the legs backwards. And so it learned how to flip over. And that was less than a dozen tries. So a simple genetic algorithm, you can learn things autonomously. So the next phase was, okay, great. You learned how to flip over. Now rise up and walk. I'll talk over this one. So this is the same thing, same algorithm. He's standing up, and now the goal is to maximize delta x, delta y but don't change the z-axis. If the z-axis either goes up or down, you know you've fallen. So basically, move but don't fall is the simple mathematical definition of success. And so it's going to try things at random. Ooh, axis down. And it learned, okay, a little bit. And so now it's going to add the next frame of animation. It's going to do slight variations because it wants to hill climb to do it better. And it slowly learns.
And it's using mutation, just like a normal genetic algorithm.
Exactly.
So it's mutating and then.
It takes the 16 values, for example, it's already learned this first frame of animation is just 16 angles of the servos. It's going to slightly rotate them or slightly change them each iteration to see if there's a better way. Because the z-axis or the z vector is moving a little bit, and it wants that z vector to be completely parallel. And so it's going to try to move and walk.
16 settings for each servo?
For one version for each servo.
Looks like, how many servos are there?
16.
Seems like a
Actually,
lot-
there's 14 because he's missing an arm.
It seems like a lot of combinations.
Yes,
Huge amount of
exactly.
configurations.
Like checkers, the search space is enormous.
Yeah.
There's a lot of bits of potential animations that you could do.
But it's kind of like you said, it's pruning and it's going and it's pruning every time.
Exactly.
It mutates so that a lot of them are discarded, right?
Exactly. I think there's a better version of this. I have to right click and say open with.
Or you could,
PNG.
it should be just
Yeah.
single click.
Here's a similar one. Now, briefly while it's doing this, you can merge these techniques. And instead of just doing randomization to hill climb, I actually put a little Bayesian classifier to decide how you should mutate. And I think this video shows an example of how that made things a little bit better. So it learned that if I spread my legs really wide, I've moved, which is what I want to do, and I've moved without changing that z vector parallel. And so now it sort of learned, and one of the features was angle between legs. Well, that's a good thing to do, so I'm going to try that more often than just randomly deciding what to do with the servos. And it will quickly learn to go spread legs, close legs, spread legs, close legs. So it's using here a Bayesian classifier to determine what is a potentially good genetic algorithm generated random next guess.
Oh, so you're using the Bayesian classifier to reduce the type of mutations in a sense.
Exactly. So even though it would learn quickly with just the genetic algorithm, using a Bayesian classifier to prune the genetic algorithm's randomization for the mutation function made it learn just a little bit faster.
And that's based on the statistics of
Exactly.
which feature changes went in the right direction.
Exactly. Let me speed this up here. I think towards, how do you...
And he does do a lot of repetition there.
Yeah, well, because he's learned what worked.
And he tries to go from there.
And he'll try to go from there, and he'll do slight randomization to get there, because it's like, oh, maybe I can get there slightly better.
Yeah.
And you'll notice when he does fall, he tends to fall a little bit slower, because the time issue is how many steps did I take? How far did I get? How long did it take me to fall? And I think this video goes, he eventually will take 7 steps in a row. Yeah, so he tried it, and there's slight variations. And here's a robot, and this is running on an Arduino Nano. So it's not a lot of data. It's not CPU compute intensive at all. Very simple algorithm, very powerful. I was laughing when Boston Dynamics was showing our robot Atlas learned how to walk and how to do things by itself. I It's like, yeah, been there, done there, that 10 years ago, on an Arduino.
Yeah, they have
so-
a server room full of,
Exactly.
A1000s, whatever.
So Thomas has a question from chat. He was wondering if you could explain genetic algorithms.
Yeah, briefly.
Okay,
Oh,
a brief explanation of genetic algorithms.
We can also refer back to a Dr. Bruce lecture from like 4 years ago, where he did words. He used text, and he had the genetic algorithm that figured out what word he was looking for from random letters.
This is sort of a brief overview of what a genetic algorithm is. And the idea is you have a random population at the top. Now, because we're using a physical robot, our population is 1. But the idea here is if you would try, let's say we had 100 robots and go back to it learning how to flip over. You would generate 100 random first poses. And then you would run those 100 simulations, and now we're here at the evaluation function. And for that particular one, the evaluation function was really simple. What was the delta z? The direction of the change of the z vector. And it would give you a single number saying, here's how we rank these 100 trials from best to worst. And then down here, selection is, we're going to kill off 95 of them, and we're going to let the 5 that did the best survive. And then we're going to take the data from those 5, and we're going to mutate them. We're going to mix and match. And you can get into a lot of details about how to do crossover and mutation, but the idea is you want to make it similar to what you know worked, because they were the top 5, and we're going to slightly modify it. And from those 5, we're going to generate 100 new ones. So each one of those 5 is going to have, 19 children that are similar to them, and then we repeat. And the idea is every time you go through this cycle, you get better and better and better. So Thomas, I hope that is a good, very brief explanation as to how a genetic algorithm works. I actually have the source code to something. I'm going to show you the demo first because we're short on time, and then I'll show you the source code. Motbot. This is a very simple robot. Here's again, I don't know how do you open?
You should just
Okay. This is a simple Arduino, 2 yellow motors, and this particular one has a ping sensor. Can I right left?
Yeah.
How do I get to the next image? Oh yeah. And so I have.
It takes time.
Oh, okay.
Or it's graphics.
So this is the version that I decided to put another genetic algorithm, and this was designed to do the tabletop challenge. So it's simple Arduino, 2 motors, and there's these 2 line sensors. So it knows when it's gone off the edge of the table. And again, the word ghetto is going to come up a lot. This is really cheap. You can see popsicle sticks and super glue.
I love it.
Is this a balancing bot, or is there
It's
another wheel?
running on a Mott Apple.
A 3?
Yeah,
It has a
It's-
caster.
it has a caster.
Okay.
I think I have a picture of the caster. It actually won the gold medal at Robo Games.
There it is.
The reason it's called the Motbot is because when I bought the parts from China, the caster didn't arrive in the packaging. And I saw that the height was about the same height as this Mott's applesauce cup as I was eating some applesauce. And so I just glued it to the bottom. And so underneath the heavy part of the battery pack is a Mott's upside down Mott's applesauce container. And people hence christened it the Motbot. So that's how it got its name. But here's all of the instructions on how to build one. And that's going to be on the Google Drive. And so now we want to do the tabletop challenge, and I thought, let's use a simple genetic algorithm so that it can learn how to do the tabletop challenge autonomously by itself. So I got a quick video of that. This is MottBot Learning with the genetic algorithm, take 1. So I'm going to talk over my self-talk video. Now, the data here is there's 4 states. Because there's 3 young sensors, there's 4 potential states, whether they're both on, both off, or one on, or the other off. And in each of those states, decides what value do I want to send to the left. So there's 3 numbers per state, 4 states, so there's only 12 numbers that represent everything about the behavior of the computer, or of this robot. And it starts off random, and it's going to slowly learn how to do the tabletop challenge. Now, as it's doing it, as you watch the video, it's important that you define properly, because the first version I said, don't fall off the cliff. What do you expect? Don't move. Exactly, that's exactly what happened. It learned to just do nothing because it realized if I tell the motors to go, I'm going to go off the edge. Move as fast as you can, and you get points for moving fast. There. Well, it knew. And as the genetic algorithm, that meant you get no progeny, you do not
Spin in a
survive.
circle.
Exactly. It learned how to spin in a circle as fast as it could. So the third version was, so in other words, don't stay in the transition where you're on the table. And that was when it finally did something. The moral of the story there is, you get exactly what you
And the point for in transition.
Exactly.
Why not just transition?
Might actually go faster. But now it's learned, okay, I'm either going to spin to get back on or back up a little bit.
Like those sensors are off the edge, but it keeps moving.
How this works is I said after 5 seconds, and then evaluate yourself. How well did you stay on the table for the or how long did it live? How many transitions? How fast motors?
Because it's always recording deaths as
Well, actually 2, because it has in its memory what its previous best was. Pick the best of those 2, and each generation only really one new potential. But it's not taking it again, it's still
that's all running on it.
Now this is all running on an nano, which is why I love this getaway. You can do this at home and you don't I guess you can do this in definition of the previous box, I'm old because I still use it.
Of course, how does it doesn't know, it doesn't have other styles people.
No,
But, it could go to any edge and still get points.
It still get points.
Okay, so sounds is the other side, right? So then you could say the longest, the
Guys?
longer you go, the yeah.
Guys, the online can't hear any word.
One edge, other edge, and back.
That's challenge number 1.
Yeah. But here I'm just going to basically stay on the table and just go at random until you find an edge.
When you've got those 2 line sensors, how do you know where his wheels is? Are you calculating something for those 2?
No, he doesn't.
So his wheel goes out the edge.
We start from the same position.
But when the edge goes up, when that sensor
All this robot knows is I'm in one of 4 states, and I'm going to look up 3 numbers when I'm in that state. And those 3 numbers are, I'm going to set the left motor to this value, the right motor to this value, and then I'm going to pick these up and I'm going to plot this node. And then I have no idea how far I'm going to go or in what direction. And then that many milliseconds later, I'm going to read the sensors again, see what state I'm in, and it's that simple.
When you back up, it'll fall off the table before the sensor
Go in reverse, but he may go reverse too far and then back up off the
Guys, we can't hear a thing.
Generating a random mutated text, and then scoring itself.
And you win first place. What about that?
Guys, we can't hear anything.
This robot was doing what it was doing with less than 20 lines of code.
Oh, wow.
And $9 worth of hardware.
Oh, okay, that is impressive.
Yeah, $9 worth of hardware, and I actually think it was 22 lines of code, and they were like, oh my god. And of course I sort of cheated. I aimed it at the objects, and so it just kind of went straight, scooped up objects and put them into the shoebox at the end.
Oh,
so
you cheated all the way to challenge 3.
It got to challenge 3 through cheating. But
But
they're like, hey, it was a great show.
And it's not reproducible either all the time, right? Like you had a good run.
Exactly.
Sometimes.
All right, so we have another question from chat from Yoshio. What are the 3 numbers to be evaluated?
Oh, he couldn't hear over the motor noise.
Oh,
We can turn
I'll
off
actually
the noise.
show you the code. Here we go. You don't have the Arduino.
You can open that in
IDE.
the text editor. Just right click
Right
and say
click.
open with Notepad++.
Oh, Arduino.
Or any of those.
And it would choose
Oh, I
the-
do have Arduino.
Or your Notepad++. Here you go.
Notepad+ is quick.
So this is the full source code to the genetic algorithm of what you just saw. And I'll quickly highlight, there's actually 3, there's a hidden sensor in the center underneath the robot. Pay no attention to that. The reason that's there is because when I initially started testing this, I was having to catch my robot as it would jump off and leap to its death off the edge of the table. And I realized I'm going to have to re-glue this multiple times. And so you'll notice I had a black board with a yellow piece of paper.
If it sees black, it's dead.
Yeah, and
Yeah,
so I
it's a simulated
have a
guess.
the center one was, oh, when you see black, shut down immediately. So that was
Oh.
my safety way and of saying, I don't want to keep gluing this back together. So that's built into the code. Reading sensors is really easy. Just digital read the sensors. And it's either a 1 or a 0. And then our state is going to be just 2 bits of state.
Want to take the comments out.
Yeah, take the comments out. So here's the genetic algorithm. It's really simple. Here's the gene. It's just a left value, a right value, and a time value. And there's 4 different states, so there's a total of 12 different numbers. And like I said, it really simply says, what's my state? Look up these 3 values in my table and set the motors and pause for this amount of time, and then continue. So the randomization was really simple. I didn't do anything fancy. I just said random. It was completely scrambled. I wouldn't completely scramble it. I would only scramble not all 12 of the values. I would only scramble a few of the values.
It's like poker. You take 1 or 2 cards.
And again, it's more art than science. Is it better to scramble 1 value, 5 values, all 12 values? There's, one of those is going to be optimal. And here's the mutation. I think I did the random of a random, so you would get some sort of Poisson distribution of random. So here's the fitness function. I won't go into that very well. It was basically how fast are you going, and did you actually find edges?
And then you gave a number.
Here we go. Yeah, for 5 seconds. So we're in this loop. As long as 5 seconds hasn't elapsed, we keep going. We just loop here, and so we just read the sensors. We get the value, and then we set the motor. And there's probably a sleep command in there somewhere to say wait. And then the iteration, again, I love it because it's very simple. You just mutate. You have the best gene so far. You mutate, create a test gene, and then you score the test gene by calling the GA fitness function, which does this 5 seconds.
So each run is 5 seconds.
Each run is 5 seconds. And then it just says who was the best. So basically, I guess you could say this is a population of 2.
It's just be better then.
Yeah, which one is better? So of these 2, I'm going to kill one of you and create a new one as a mutation of the better one.
So a lot of times they probably stuck with the same one and then mutated it again.
Yeah.
And like that was a bad mutation. I'm just going to redo.
Just redo the old one.
Yeah, and then sometimes it would go, oh, this is better. I'm taking it.
Yeah. Now it wouldn't actually redo the run because if the best had, say, a score of 7 and the mutation came out 6.9, it would create a new mutation and run that mutation.
Well, that's what I mean. It always is creating a mutation, but it was creating a mutation off of the same one twice in a row.
Yeah. So that's it in a nutshell. So that was a really brief overview of genetic algorithms that you could use on an Arduino on a simple robot for $9, and how you can play around with Bayesian recognizers to just do really simple statistical things and get really, really amazing results with just 0 CPU and 0 data and $0.
Thanks. We have another question from chat from Thomas.
Yes.
Do you save the data after each run, or do you start from scratch every time you turn it on?
Every time the Arduino power is on, it forgets everything, which is why you'll notice that I'll talk while I'm running that.
NVRAM or something to remember it.
I'll just, for fun, run some other videos. Using the same algorithm, this was a competition that I entered in with, was trying to get drones to autonomously fly through obstacle course.
Yeah.
And using a simple genetic algorithm, again, using a Bayesian recognizer to realize what's a good way. And it had this sequence of gates that it had to fly through. And it was just a control of this drone. Again, it only controls the speed of the 4 rotors of the drone. It had an IMU feedback, so it could tell its gyro and accelerometer to figure out where it was. And okay, here there, it crashed. So here's a version.
That's a real drone, or?
No, this is in a simulator.
Okay.
Which simulator?
This simulator is
Nice
called
one.
Flight Goggles.
Like, oh, that's what
And you'll notice, see right there, you notice the drone rotated before it got to the gate.
Yeah.
Because it learned, oh, this is a really sharp turn. And it started off, I go through the gate, and now trying to make that turn, it didn't work. See here, it's trying to find this gate, it's trying to turn, oh, I can't get to the
How does
gate.
it know?
Ignore
which
it,
gate
I'm
to
gonna
go
go to
to?
the next gate.
How does it know which gate to go to? And how does it know that
Colors?
it actually went through the gate? Or that part
The
of
gate
like-
sequence was given to it,
It's,
and the X, Y, Z coordinates of the gates were given to it. Okay. So it just knew I have to go through these gates in order.
And the XYZ coordinate as well.
Yes, because you're a drone, so you're in 3 dimensions.
Yeah.
So it took it a while. I want to show that again because
this had a few more numbers involved, right? Because you
yes,
guys talk
quite
about,
a few more.
talking about
Again, I'm double
10
clicking and
yeah.
it's not playing. How do I play the
Just-
video? It's
just
kind of
single
there we go,
click,
yeah.
single click.
So it
always.
finds the first one. So here's the gate with the sharp hairpin turn, and you'll notice it actually turns. It learned that its momentum will carry it through the gate.
Oh,
And I thought that was cool. When
that's
it,
what real
when it
pilots
learned-
do.
when
I
it
think.
learned
Know
how to
about
do
the
that.
obstacles?
pardon?
Does it know, can it see those obstacles?
No, it doesn't know. It has no data about the obstacle.
It only knows.
It only knows where the gates
are.
are. It only knows where the gates
Sorry,
are.
the middle of the XYZ's in the middle of the.
Yeah,
the
so it
gate.
does crash into obstacles, and it does learn, oh, I missed it, so go on to the next one. Because it realizes it's scored for how many gates did you make, and what is your time. And so it learns, for example, is this the one? Where's the one where it kept circling around the gate and it just couldn't get through it because of momentum?
Yeah,
And then after a certain amount of time, it realized, I'm losing points. Let's go on to the next game.
Wow, that's quite.
But that's
invention.
that's why I want to impress with such a simple algorithm. With a few lines of code, you can get these really beautiful, complex behaviors without, again. And I like it because it's hands-on. It's one thing to use ChatGPT, for example. I like to build it. I don't like to use what other people have done. I like to do it myself.
Even if it's, just a simple thing, not this multi-billion parameter thing with trained for millions of dollars.
Yeah. So
Oh,
that's
really cool.
pretty much it.
Are you gonna have links to some of these resources or something?
Yes.
Or we can look at them later?
You can
I
post
have
it
all
or-
of these
Yeah, yeah.
pictures and videos